Today we start our new unit, we call it dynamics. We define kinematics at the beginning of the year as the study of motion without regard to what causes the motion. And a few times we alluded to what does cause the motion, but we said we'd leave that for the next unit, our next unit called dynamics. Dynamics is the study of motion as well, but it's with regard to what causes the motion. So we'll say it's the study of motion with regard to what causes the motion. What is it that causes the motion? One word. What causes motion? Yep. Force, right. So in other words, we're going to say that dynamics is the study of forces. Now, we're still going to use our old kinematics equations, like Vf squared is equal to Vi squared plus 2AD, and V is equal to delta D over delta T, and so on. We need to look at the motion itself, but we're now also including what causes the motion, or the forces that cause that motion. Now, we're going to define a force here. You've probably already done that before, back in, I don't know, grade 6 or something. I know you learned about flight in grade 6 and talked about the lift force. You remember the lift force and the drag force, right, and the thrust force? Remember that? You probably would have defined a force back then. Does anybody remember what a force is? It's a quick, short answer, and it's easy, and it doesn't change from grade 6 all the way through grade 11, grade 12. A force is a force. However you define it then is the way we define it now. A force is a 3 or 4 words. Yeah? No. You were about to say it, I think. No, it looked like you were about to say it. A force is a, like you're, I have no clue. A push or a pull. A force is a push or a pull. That's it. There's 4 fundamental forces that we talk about in physics. We won't get into, for the most part, those fundamental forces. But in the end, all of the other forces that we have, and there's millions of different kinds of forces, but all of those millions of different forces correspond or boil down to 4 fundamental forces, 4 types of pushes or pulls. We define a force as a push or a pull, but we say that there's a couple of different things that a force can do, that a force can accomplish. Well, we know what one of them is because we talked about it just a second ago. What's one thing that a force can do? It can cause things to move. In other words, it can cause things to accelerate, to start. It can cause things to stop as well, right? It can cause things to speed up. It can cause things to slow down. And in fact, a force can also cause something to change direction. If you're walking along the front of the room like this and I give you a push, you're not necessarily going to speed up or slow down, but you change direction. Do you know that even if the object isn't speeding up or slowing down, if it's changing direction, it's still accelerating? It's still an acceleration because acceleration is based not on the change in speed, but the change in velocity. So what we're going to say here is that a force can cause acceleration. Which can mean speed up, slow down, start, stop, change direction. A force can do any of those things, which are all lumped together under acceleration. But you know what? It doesn't always cause an acceleration. If I was to, let's say, take one of those big exercise balls and sit on it, I'm applying a force on that exercise ball, right? Clearly, I'm pushing the exercise ball. I'm not causing that exercise ball to accelerate, though, right? It's on the floor. I'm sitting on top of it. It doesn't go anywhere. So what happens to the exercise ball? What's the effect of the force in that case? Pardon me? Yeah, we're causing it to deform. Okay, it can compress the exercise ball, or maybe sometimes you're pulling on something. You know, you're pulling on someone's sweater, and it doesn't cause them to accelerate because they don't go anywhere, but yet you're stretching them. You're making them wider, right? So you cause a deformation, a change in shape. Is it ever possible, do you think, for a force to do both? To cause a deformation and an acceleration? Sure it is. Sure it is, right? When I bounce a basketball against the floor, the floor pushes up on the basketball. Otherwise, why would the basketball start going back up, right? The basketball has to have a force applied on it by the floor upwards. That force causes an acceleration of the basketball. It causes the basketball to slow down and then very quickly thereafter to speed up so that it can go back up into the air. But it also causes the ball to compress, right? To deform, a deformation of the basketball. So yeah, there's lots of situations where a force can cause a deformation and an acceleration. Who plays golf here? Who's a golfer? Do you know that when you hit a golf ball with a golf club, if you hit it well, the golf ball for a short period of time, for a brief moment in time, actually compresses to about half the thickness of a normal golf ball? If you were to take super slow motion video, like 1,000 frames per second video of a golf ball being hit by a driver, the golf ball would become barely half the size, half the thickness that it normally is. You don't see that because it happens so quickly, but that's what happens. The golf ball clearly deforms a lot, but obviously the golf ball also accelerates quickly as well, because all of a sudden now it's moving down the golf course 300 yards, 200 yards, whatever the case may be. So it experiences an acceleration and a deformation all at the same time. Another term, net force. Net force. What does net mean? Forget about force for a second. We know what that means. Push or pull. What does net mean? Total? Yeah, good. Total. It's the total force. We'll say the total unbalanced force. Total is the big word, though, right? Because total force, when we calculate a total force, sometimes it's not actually unbalanced. Sometimes the total force is balanced. So let's say I've got a force of 10 newtons to the right, a force of 5 newtons to the right. Well, the total force would be 15 newtons. But if I have 10 newtons to the right and 10 newtons to the left, the total force is 0 newtons. And then therefore we would have a balanced force. Net means total, the total, in this case, the total force. Like my net salary is my total salary. How many people have a job here? How many of you guys work? You get a pay stub. Your net pay is your total pay. After they figure in how much money you make for your hourly wage at what do you guys make now? Like what's minimum wage? Like $13 an hour? $13.60 an hour? Okay. So they figure in like 10 hours at $13.60 an hour is $136, right? But then you get vacation pay as well. Sometimes it's included on your pay with each pay. Sometimes you get it at the end of the year. Let's say it's included on each pay. They add in your vacation pay. But then they add some negative numbers as well. Like maybe they take off, depending upon how much you make, some income tax. Maybe they take off some employment insurance. Okay, maybe they take off some kind of fund for staff parties or something. Maybe they take off different stuff as they add negative values. They add positive values to it. When your pay goes up, they add negative values. And in the end, at the bottom of that pay stub, it says your net pay is whatever. Like for instance, my net pay, okay, when they pay me for the month, my gross pay, by the way, you see that term gross at the top of your pay stub? That should be the term that's at the bottom of the pay stub, right? Because it should be, by rights, because when I look at my pay stub, I like the number at the top. But the number at the bottom, after they take off all this money for employment insurance and Canada pension and stuff and income tax, that's the gross number when I see what I have left after all that stuff. But in the end, technically we say the net pay is the number at the bottom. If I make, let's say, $500, and then I make an extra $100 because I did something special, because they like me. But then they take off $200 for tax. And then they take off $150 for employment insurance. And then they take off $200 for something else, for my pension. And then they take off $50, well, just because they realize they made a mistake. They didn't like me as much as I thought they did. Add them all up. 500 plus 100 is 600. 400. 250. Oh, look, I'm back down to 0. So my net pay in this case would be 0. Does that make sense? That's what it feels like sometimes when I get that pay stub. Is like, hey, that number at the top looks good. Not exactly $500, but it looks good. But then I see all those negatives on there, and then it starts looking a little gross after that. Make sense? Total or net force. Another term. Man, terms coming out the non-stop here. Inertia. Everybody's heard this word, right? Because in junior high school you watch Bill Nye the Science Guy, even though it's old. They haven't made Bill Nye the Science Guy in like 20 years. Inertia is a property of matter. Does anybody know what inertia means? Probably not. It's a tendency of an object to resist a change in motion. A tendency to resist a change in motion. What do you think affects the object's tendency to resist a change in motion? What do you think it makes, what property of an object makes it more difficult to change the motion of that object, Luke? It's mass, yeah. So the inertia of an object depends on mass. And mass is the amount of matter that something possesses in kilograms. It's not the weight. The weight of an object is actually a force. The mass is the amount of matter that it possesses. And the mass doesn't change no matter where you are in the universe. If I'm on Earth or the moon, my weight on the moon is 1/6 of what it is on Earth, but my mass is exactly the same. Okay. I have a mass of about 70 kilograms on Earth. I have a mass of 70 kilograms on the moon. I have a mass of about 150 on Earth. Sorry, a weight of about 150 pounds on Earth. I have a weight of about 20-something pounds on the moon. Quick way to lose weight, right? Go to the moon. Want to lose weight? Go to the moon. Problem is, if you come back, you gain your weight right back, right? You lose 5/6 of your weight. You lose 84% of your weight when you go to the moon. But then it's one of those yo-yo diets, right? You gain it right back when you come back to Earth, unless you want to stay on the moon. Static equilibrium. Who takes biology class here? Chemistry? Some people take both. All right, good. Have you heard the term equilibrium in biology or chemistry? Equilibrium, what does it mean? Equal? Yeah, okay, stops going both directions, kind of reaches, somebody said it, a balance? Yeah, so it reaches a balance, sure. When something's in equilibrium, something's balanced. We're talking about dynamics in this unit, which is the study of forces. So we're talking about balanced forces here. So when it's in equilibrium, the forces are balanced. What does static mean? Still, not moving? So when something's in static equilibrium, we have an object at rest. An object is at rest. That's the static term. That has balanced forces. That's the equilibrium term. If it has balanced forces, what's another way of saying that? There is no unbalanced force, or the net force is what? Force is balanced, the net force is 0. So if an object is at rest, the forces must balance. That doesn't mean there's no forces. Hey, that desk right here, right in front of Ryan, that desk is at rest right now, right? But there's two forces acting on that desk right now. Force of gravity is pulling down on it. It's not moving though, so there must be a force pushing up on it. There is, in fact, the force of the ground or the force of the floor pushing up on it. We call it the normal force. But those two forces must be equal. So if the force of gravity is 200 newtons acting on that desk, then the normal force pushing up is 200 newtons because they have to balance each other. An object at rest has balanced forces. What does an object at rest want to do? Wants to stay there. Wants to stay at rest. Okay, you're sitting there watching a baseball game. No, that's a bad example because you guys don't watch baseball, do you? You should, because it's way more interesting than you guys think. But you're sitting there watching a hockey game on the couch, okay, with some nachos beside you, okay, a big 2-liter bottle of Coke beside you, sitting there at rest. Mom says, go clean your room. What do? You don't, because an object at rest wants to stay at rest, right? An object at rest wants to stay at rest until your dad comes over and grabs you by the arm and lifts you up, says, go clean your room. Do what your mother says. An object at rest wants to stay at rest until some outside or unbalanced force causes you to start moving. Translational equilibrium, well, equilibrium again, balanced forces. Translational means moving. So this one we'd say an object, a moving object with balanced forces. A moving object with balanced forces. So you're driving down the highway. Do you know that when a car drives down the highway, there's all kinds of forces acting on that car, right? Gravity acts down on the car. There's the normal force, that force of the ground pushing up. If there wasn't, then the car would just fall down. If there was nothing to balance it, right? Horizontally, the car's at rest. Vertically, I mean the car's at rest. Horizontally, it's not. Horizontally, it's moving. But you can be moving at 100 kilometers per hour on the highway, and there's lots of forces acting, including air resistance, a lot of air resistance, right? You ever try sticking your head out the car window at 100 kilometers per hour? There's a lot of air resistance, force pushing you back. But there's also that force of the wheels pushing you forward. Okay? Well, if you're going at a constant speed, then those two forces have got to balance. You're in translational equilibrium. An object that's moving has balanced forces. Hey, what do you think an object that's moving with balanced forces, an object in translational equilibrium wants to do? An object at rest wants to stay at rest. An object that is moving wants to keep moving. Wants to keep moving. That car that has balanced forces will keep moving forever in a straight line at a constant speed until some unbalanced force causes it to slow down or speed up. But wait a second, I'm going to run out of gas eventually, right? And then I'm going to stop, right? Yeah. Okay, that's when the force of friction slows you down and you have nothing to balance the force of friction to keep you going. That's when we have an unbalanced force. You're never going to stop moving in a straight line at constant velocity until you have that unbalanced force. Make sense? We're going to summarize that with one law here that we call the law of inertia, Newton's first law, which says, basically has two aspects to it. An object at rest will stay at rest until acted upon by an unbalanced force. Look, it's in static equilibrium. And of course, the second part of it is an object in motion wants to stay in motion. We'll stay in motion, but not just any random motion, in a straight line, constant speed. So it's not going to speed up, slow down. It's not going to change direction until acted upon by an unbalanced force. That's in translational equilibrium.